Hi everyone, Mr. Lee here. In this review video, we are going to go over simple harmonic motion, both the pendulum version and the spring version. All right, let's get started. So simple harmonic motion. Now, if you remember from the unit, there are two main equations for simple harmonic motion. We're going to go over both, but more importantly, I want to focus on the big concepts behind simple harmonic motion and the types of problems that you might encounter when you take the exam. So the first one I want to show is the period of a pendulum. So the period of a pendulum, or period in general for both of these motions, spring or pendulum, they rely on this 2 pi, right? This is my pi symbol. It's equal to the square root of L divided by G. Now, I think, for me at least personally, the hardest part about this idea is when we talk about the relationships, right? So what we're taking a look at here is a squared relationship. Now I'm going to do a mathematical little trick here with this equation. Now this is the equation that you'll see on the equation sheet, but what I like to do is to really help with my mind at least, I like to square everything. So I get 2 pi, or excuse me, period pi squared is equal to 2 pi squared, so that becomes 4 pi squared. And then we have L divided by G. Now the reason why I like to do this is so that I can see the relationships a little bit more clear. All right, now before I do the relationships, just as a quick reminder, the period of a pendulum is when you get a pendulum and it swings back and forth, and the period is how long it takes to go from one spot to another and back. Okay, so that's one full cycle, so forward and back, right? So that's one period, so how long that takes. So if we take a look here, the period of a pendulum depends on two variables, right? And that is the length of the string and the gravitational acceleration. So if you were to perform an experiment on the moon where there is less gravitational acceleration, you'll get different data than if you were to do it on Earth. So the relationship is as follows. So the period of a pendulum versus the length of a string. So here we have a square directly proportional relationship. Okay, and we know it's squared because within the equation we see that TP is squared. Now, if we were to compare it to this right here, we can say that it's a square root as well, where the square is talking about the period, and the square root is talking about the length. Okay, and if we were to take a look at TP versus G, we would say that this is the inverse square. Okay. Now the important thing here is that you know that there's some form of squaring going on, and that the length is directly proportional, and that the acceleration due to gravity is inversely proportional. Now, for me personally, the hardest part about this is, what does this actually mean? You know, if it's directly proportional. So if the length increases, I can tell you that the period of a pendulum increases. Okay, but the meaning behind it, what does that mean? And I like to actually say it out loud just so that it makes sense to me. So when the period of the pendulum increases, the time increases. Okay, so it takes a longer time. I don't know why, but for whatever reason, I always think that when the period of a pendulum increases, it takes a shorter time. But if that's just me, if that's you as well, just know that you're not alone. Okay, so I have to actually say it out loud, and I have to actually write it down to remind myself that if the time increases, or the period increases, it takes a longer time. Okay, so that could mean a myriad of things. It could be moving slower, or whatever the case is. So the inverse is true. So if the acceleration due to gravity increases, then the period of pendulum that decreases. So this is a shorter time. So it could be moving faster because the acceleration due to gravity is pulling in on it a lot more. Okay, so there's a couple of things that we can go over here, and before we do the idea behind springs. So the reason why the period of pendulum goes back and forth is because we say this force of gravity, right? This force of gravity is pulling on it downwards, and we say that there's a tension force, right? It's because this tension force is at an angle. We can say that the X and Y components of these tension forces, that's what's really driving the back and forth motion. More specifically, this Y component of the string is what's equal to the force of gravity, and that is something that you need to know, right? This Y force is the force of gravity equivalent. So that's not what's making this move to the right. The one force that is accelerating this object to the right would be the X component, this Tx. Okay, so this tension in the X direction makes this object move to the right or accelerate to the right. okay? Because this vertical component, it doesn't do anything. It just holds it in place. So here, when it's right in the middle as it's swinging back and forth, you'll notice that the tension force is vertical and this force of gravity is down. So there is nothing that is pushing it left or right when it's just there, okay? It's just a momentum that carries it left and right. But when it goes over to the other side, same as the inverse here, the X tension pulls it to the left, okay? Whereas the vertical component of the force, right, this Ty, is just holding it in place compared to the F of G. All right, so with this being said, there's a couple things that you need to know. I'm going to call these different positions. I'm going to call this position 1. I'm going to call this position 2, right in the middle. And I'm going to call this position 3. Okay, so at position 1, you need to know this is the max height. Okay, we have max height. So if we have max height, we have max gravitational potential energy. So if you have max gravitational potential energy, you have no kinetic energy. Okay. All right. At position 2, you have minimum height. So if you have minimum height, you have no gravitational potential energy. If you have no gravitational potential energy, you have max kinetic energy. And position 1 and position 3, they're the same, but I'm going to write it out. Position 3, you have max height, therefore you have max gravitational potential energy, and you have no kinetic energy. So what this means is that you have no motion at positions 1 and 3. So if you remember when I first introduced this, we went over a multitude of graphs. I'm just going to do a really quick sketch of a position time graph and velocity time graph and a acceleration time graph. But this is what you need to know. You should definitely go back and look at those videos and watch how we go in depth with this. So I'm going to do a simple, not a harmonic motion, but a simple curve like so. Okay, so we have a simple curve here. A couple things that you need to remind yourself. For a position time graph, okay, position versus time, the slope, okay, remember slope is a division, position versus time gives you the velocity. So we're taking a look at the velocity if we're taking a look at the slope. Now, the parts you need to identify. Where is the slope 0? There, there, and there. Let me just make that a little bit more clear. So when the position is 0, that means you have no kinetic energy, no KE. No KE, okay, no KE. So at these 3 positions, you can either be at positions 1 or 3. 1 or 3. And that's because there's no kinetic energy at these 3 positions. All right, so if I'm taking a look at this graph, it's important for you to know that as I'm going for, let's say I'm going to call this position A, this is position B, this is position C. As I'm going from A to B, notice how going from A to B, my slope is negative, okay? And so whatever that means to you in your graph, it just means that I have a negative velocity. So this could mean that I'm moving to the left, okay? So this is me going from 3 to 1, all right? Now here, I'm gonna do a different highlighting color. This is what you need to be able to identify. This is actually very important here, right there, okay? When X is going through that middle position, if we know that there's no kinetic energy here, no kinetic energy here, we can say that here we have max kinetic energy. So if you remember, we have maximum kinetic energy right in the middle. So this is definitely position 2. So it goes from position 1 to 2 to 3, right? And then we can go back here to be 2. This is position 2 because it has max KE, okay? And then it goes back, right? Actually, it'll be 3 to 2 to 1, back to 2 to 3 to 1, 2, 3. That's how it will go. All right, so this is for position versus time graph. Next, if we were to have a velocity time graph, okay, I'm not referencing this first graph anymore, right? I said everything I could. So if I have a velocity time graph, right, same shape, you should be able to identify a couple of different things. One, always identify the zeros. When your velocity is 0, that's where things are important. Just like here, we identify where there is no velocity, right? When there's velocity is 0. That's what we were looking for. Those are the yellow highlighted parts. When your velocity is 0, I'm going to highlight it once again in yellow, to keep up with it. Velocity yellow there, velocity yellow there. Okay, that's where we have no velocity. How do we know that? Well, the y-axis represents velocity, and there represents 0. So I have no velocity there. So at those 2 points, remember, we're not referencing this first graph, right? We're done with this first graph. This is a brand new scenario, brand new data set. Here we have positions 1/3. Okay, 1 or 3. Here we have 1/3. And we know that because we said at positions 1 and 3, there is no motion. There's no kinetic energy. So that leaves us, and I'm going to do this in green, with the other main parts, there, there, and there. That's when we have max. We have max velocity. Here we have max velocity. Here we have max velocity, albeit negative, but it's still a maximum velocity. So remember, if you have maximum velocity, you have maximum kinetic energy. Maximum kinetic energy. Okay? All right. So we have maximum kinetic energy according to our chart only at one spot, and that is position 2. So here we have position 2, here we have position 2, here we have position 2. All right. So that's how we can go from a velocity time graph with reference to our little drawing there. And you know what? Let's end with acceleration versus time. Okay, acceleration versus time. Now these are a little bit more trickier because we don't really take a look at acceleration versus time graphs a lot, but we should be able to do the acceleration versus time graph too. Okay, I'm going to create the same shape. Remember, this is just a shape to take a look at the max and the mins. In no way are the 3 graphs related to each other, but we got this, right? We have acceleration versus time. So for here, what you have to identify is when do you have maximum acceleration. So I'm going to highlight it. Highlight in yellow. We have maximum acceleration here. We have maximum acceleration here. We have maximum acceleration here. Okay, for the yellow parts. Now, let's take a look at this diagram. So we have acceleration. So if I were to question mark acceleration, question mark, where is the acceleration? We only have acceleration when we have a net force, because F equals ma. So if I take a look here, the only times when we have a net force is when we have positions 1 and 3. And that's because at position 2, the tension and the force of gravity, they just cancel out. There's no net force. But at positions 1 and 3, we have these red X components, right? These red force components. So that's when the pendulum, even though it's not moving, remember acceleration doesn't tell us that it's moving, that's when it has the most acceleration. So at these points, at those 3 points, we'll say this is either position 1 or 3, 1 or 3, 1 or 3. Now hopefully by this time you're getting the hang of it, right? So if these maximums are 1 or 3, that means that when it's crossing through the middle part, that'll be whatever we left out, and that'll be position 2, right? Those are position 2s. Now if we take a look here, right there, that position and this position right here, the 2 green ones, what that tells us is that your acceleration is 0. I'm going to highlight that as green. Okay, so we have acceleration of 0 at those 2 points, okay, whatever that time interval is. Now we said that's at position 2 right here when it's vertical. That is true because our net force is 0. The tension and the force of gravity, they cancel out, so you have no net force. Remember, it's just the momentum of the pendulum that keeps this object going. All right, so we have that. Before we get into springs, I just want to go over a couple of different things that you might see. So if you see something like a I don't know, like a position time graph, right? And you need to determine, let's say you need to determine the period, right? Because period is like, you can think of it like time. It's not time, right? But you could think of it like time. It's kind of, right, like time, where it's the units are still in seconds, but remember it's when it starts to repeat itself. So for here, 1 full cycle, I'll highlight this, is when the shape, when this sinusoidal shape starts to repeat itself. So here, go up, go down, and boom. Once we stop right there, that is 1 period. And so in order to determine the period of this graph, we would just see how long that took. What was that time? And that time will give us 1 period. Okay. Now, with that being said, you need to know that frequency is 1 over the period. So if you ever see the term frequency, know that all you got to do is find 1 period and go from there. The units for frequency is hertz, Hz. Okay, and that's after the scientist, I think his name was Frederick Hertz. I think so. All right. Another thing that you should be able to do is, especially when it comes to like a velocity time graph, right? Velocity time graph, we take a look at that, right? The same, it all holds true, right? When it starts to repeat itself, that is one full cycle. So here we start off with no velocity, and then we went positive velocity. So positive velocity, positive velocity, positive velocity to no velocity. Okay, so we went from a no velocity situation, okay, no velocity situation here and here. So those are at the two ends of the swing, and then it starts to have a another. Okay, now we have negative velocity, and then we go back to no velocity right here. So this would be one full cycle because we're going back to a positive velocity there, so it starts to repeat itself. So you would see how long this took, and then you should be able to go from there. Okay, all right. So that is going over period. We went over frequency. The next thing I want to show you is the springs. The springs. Oops. The springs. So for springs, the equation is T sub s is equal to 2 pi square root of the, let's see, what's the mass? Okay, divided by the spring constant, m over k. All right. So for something like this, you might come across a problem where you need to find the spring constant. And if that's the case, you got to use the force of the spring equation. This is called Hooke's law. Force of the spring is equal to k times the displacement, or how far it's being pushed slash pulled. So I'm going to put this off on the side, but I want to focus on this equation right there. Notice it doesn't matter. Okay, this is very much like the equation for a pendulum. Okay, it doesn't matter how high up, let me drag it a little bit more. It doesn't matter how high up you release it. Okay, the only thing that matters is the length and the acceleration due to gravity. So notice here, x is not a part of the equation. It doesn't matter how much you compress it or how much you stretch it. The only thing that matters is how much mass is attached. Okay, how much mass is attached, or how strong that spring is. So let's just go over the relationship again. This is a square directly proportional relationship, and this is a square inversely proportional relationship. Okay, and we know that because this mass is in the numerator, and so is the spring, and this spring constant is the denominator, but this spring constant is, or the period is in the numerator, so it has opposite effects. All right. Now this should make sense because if you attach a more massive object to a spring, the spring's gonna have a harder time pushing and pulling on it. So it's gonna, like, the more mass you have, so more mass, well, let me just use that, right? So if you increase your mass, the period will increase. Okay, and it's because it takes a longer time. Now once again, I have a really difficult time, I don't know why, but my brain just has a really hard time understanding that more period means it takes a longer time. Okay, for whatever reason, I think that it means a shorter time, but it doesn't. Okay, as your period increases, that means your time increases. So if you think about it, if you attach a more massive object to a spring, it's going to have a hard time, pushing it back and forth. So it's going to take a longer time for that to happen. And for here, the inverse is true. So if your spring constant increases, right, if you get a super strong spring, that means the period will decrease. It's an inverse relationship, right? So if the spring gets, like, super buff, right, it can make that mass oscillate faster. So it takes a shorter time. So it takes shorter time. Okay, so that means it just goes back and forth quicker. Okay, all right. Let me see. Okay, the last thing that we want to look at is a energy versus time graph. Now, for a spring or a pendulum, the ideas hold true. So I'm going to do a quick sketch with the spring one because we didn't do that. I'm going to do 1, 2, and 3. Right, so we have, so this is just like different times. I'm just doing it vertically from each other so that we can compare it easily. All right, so this is the surface. This is my spring. Let's say for position 1, it's like fully extended. This is max extension. This will be the equilibrium point. Okay, number 2, middle is at the equilibrium point. Okay, and number 3 is like really freaking squished like that. Okay, so here, much like the pendulum stuff, there's no motion, no velocity. Okay, if there's no velocity, that means there's no kinetic energy. Okay, this is max spring potential. Okay, and much like the pendulums, 1 and 3 are the same. There's no velocity here. There's no kinetic energy here. You only have max spring potential. Now, you need to know why. Okay, spring potential energy is 1/2 kx squared. The reason why you have max spring potential energy there is because this x, okay, this is the displacement from equilibrium. Okay, so that's just a really fancy way of saying how far did you stretch this thing, or how much did you compress this thing from where the spring naturally wants to be. And so here, this diagram for number 2, that's where the object wants to be. It wants to be sitting right there, but we're like, no, we're going to move you from your comfort zone. We're going to stretch you out, or we're going to compress you. Okay, so that's why here there is no spring potential, but we now have max kinetic energy. So it's actually moving the fastest. It's the fastest right there, right in the middle. Okay, fastest. I don't know why they gave me a triangle there. All right, so yeah. So here, what we can do, and the other graphs hold true, but what I want to show you is a energy versus time graph. Energy versus time. Why did I make it so big? I don't know. We have an energy versus time graph. Now, there's 2 things I want to show you. One, there can be I'm going to do 2 different color lines. Okay, and if you don't have different colored utensils, use like, I don't know, dotted lines or solid lines or whatever. You need to know, okay, according to the conservation of energy theorem, the only way that energy can leave a system is if there is friction, okay, heat, or if there's an outside force. And we usually say friction is that outside force. Otherwise, your total energy, your total mechanical energy, energy stays constant. Oh my gosh, stays constant. Now, you see that this is a horizontal line. What this horizontal line entails, so this could be for springs, this could be the spring potential plus kinetic. Okay, if it's for a pendulum, it could be gravitational potential plus kinetic. Whatever your situation is, okay, this has to remain constant. Because if this is not constant, that must mean that there's an outside force, or there's work being done to the system. So if this is like decreasing for whatever reason, that means energy is being lost. All right. Now, if I were to do on the same graph, let's say, excuse me, I don't know, energy spring potential, right? So this could be either spring potential or gravitational potential energy. We can start off here, and it would oscillate like this. Sound effects do help with physics problems. Okay, so notice here we have maximum here, maximum there, so max. And here we have the min. So whenever you have a minimum of a potential energy, that's where you have a maximum of the kinetic energy. All right, and I'll draw that in, do this here. Okay, so when you have maximum potential, you have no kinetic. So down here, when you have minimum potential, you have maximum kinetic. So up there, and it just bounces back and forth. Right, so, oh boy. Alright, well, that's pretty ugly, but you get the gist. Now, here's something that you also need to know. If you have damping, right? Damping means that energy, it can't go back and forth forever. Heat is generated, right? There's friction involved, and so what we get is this damping motion, and that damping motion will make it so that it doesn't go back up as much. It kind of decreases like this, much like the decrease in the volume of my voice, like so, as time goes on, like this. Okay, until there's no energy. So this will be like an energy time graph. All right, so this is what we call damping. Dampening, one of those. All right, so this just shows us that over time, the potential energy is constantly decreasing. All right, and therefore this right here, this dotted line, that'll show you your mechanical energy that decreases as well. All right, there was a lot that was there, and this is simple harmonic motion with Mr. Lee. It was a short unit for us. It was about a week, but there's so much to it. Make sure you take the time to really go over it. If there's any other videos that you need to look at before the exam, I do encourage you to do so. Bye-bye.